Okay, well, good morning, everyone, physically present and online. So today it's my pleasure to have Zoe defend her master's thesis. Zoe has been working on this for 2 years, starting the day she joined CGTC, where I asked her to start working on a website and go collect some data. And she wonderfully accepted every challenge since then. That leads us to today defense presentation. So I just want to recognize and acknowledge Legna Torres Garcia, who is online. I see you, Legna, and Hilary Loman, who is also online. Yep, I see you, Hilary. Both mentors.
Thank you.
Both mentors and advisors providing a lot of information on running models, on understanding the field and understanding administration and management of the system in the territory. Hilary, Legna, Zoe and I met in Puerto Rico probably a bit more than a year ago, discussing a lot of what you're going to see today and future work to come. So it's my pleasure to have Zoe present the work and listen to the wonderful story that she provides. Zoe, go ahead.
Thank you, and thank you for being here, everyone. I'm just going to share my screen. Okay. So thank you all for being here today. I am going to go over my master's thesis project, Shoreline Status in the US Virgin Islands, Assessing Stability and Filling Data Gaps. So first I want to go over why beaches are so important. Beaches provide a place of recreation. They are a gathering place. People have parties, celebrations there, work out, meet up with their friends. They essentially serve as community parks. Beaches are also a cornerstone of the economy in the Virgin Islands, with tourism making up such a large portion of the GDP here, and beaches being one of the main reasons that people come to visit the Virgin Islands. They really are one of the most important economic assets to the VI, and it's important that we protect them. And then finally, beaches serve as a form of coastal protection. This is arguably one of the most important ecosystem services that they provide us with. They are the first line of defense for everything behind them in the event of coastal hazards like a hurricane or other sort of major storm. And without beaches, buildings and people, homes, everything behind those beaches are at risk of coastal threats. So they're extremely important. So obviously, beaches are important. We want to protect them. We want to preserve them. But what is it that we're protecting against? So we really want to avoid erosion and loss of beach width due to factors like sea level rise, hurricanes, and coastal squeeze. These are all very much linked with climate change. As temperatures rise and glaciers melt, the sea level rises as well. This can heighten the impacts of various coastal threats, as well as cause the actual shoreline to move further landward. Additionally, warming air temperatures and sea surface temperatures create an environment in which more powerful hurricanes can form. This is also not good for beaches. And then finally, there's something called coastal squeeze. So when beaches do erode and that shoreline starts to retreat, beaches naturally want to retreat landward as well. So while the position of the shoreline may be moving, the actual width of the beach remains the same because it naturally retreats landward. However, this process cannot happen if there is too much development and gray infrastructure behind the beach. If there are buildings or walls or any sort of gray infrastructure there, the beach essentially gets stuck between what's behind it and the erosive forces in front of it, which leads to it becoming more and more narrow as it continues to erode and prevents it from actually being able to retreat. So now we know why beaches are important and what is threatening them. I want to talk about the current policies relating to beaches here in the Virgin Islands, starting with the Open Shorelines Act. The Open Shorelines Act essentially defines public beach and states where development can occur. So this defines public beach as the area along the coastlines of the United States Virgin Islands from the seaward line of low tide, running inland a distance of 50 feet, or to the extreme seaward boundary of natural vegetation, which spreads continuously inland, or to a natural barrier, whichever is the shortest distance. So this essentially states that the maximum distance of public beach available on any beach in the Virgin Islands is 50 feet. If there is a vegetation line or some sort of natural barrier like a cliff or boulders that occurs before that 50-foot mark from low tide, that would be the area of public beach that you can access, and anything behind that can be developed. Next, I want to go over the Coastal Zone Management Project, or CZMP. This was codified in 1978 and was part of the larger United States Coastal Zone Management Project that required states as well as territories to create their own CZMPs. The Virgin Islands CZMP aims to protect, maintain, preserve, and where feasible, enhance and restore the overall quality of the environment in the coastal zone, the natural and man-made resources therein, and the scenic and historic resources of the coastal zone for the benefit of residents of and visitors of the Virgin Islands. So the CZMP is a really large policy. There's a lot within it, but it essentially establishes what the coastal zone is and what can and cannot occur within the coastal zone. And one thing I want to mention is that the mainland states CZMPs were able to be informed by beach data and shoreline data that the states have access to. However, here in the Virgin Islands, there is limited data on sandy beaches. So this policy is more so based off of good intentions and ideas, but it could absolutely be bolstered with more beach data, which brings me to the issues facing beaches in the Virgin Islands. Data gaps are an issue with beaches here. There is a lack of knowledge on the basics of beaches, their geomorphology, which beaches are eroding, which are retreating, where are the most vulnerable areas, where are the most stable areas. And this leads to a lot of speculation about beach stability and the adequacy of policies. You'll hear people talk about, oh, I've been going to this beach for years and I swear it looks the exact same, but then someone else will say, well, I've been going there and I think it looks eroded. And in addition to this, current research on VI beaches tends to be very alarmist. A lot of papers calling for economic collapse and widespread, like, major beach loss in the future. However, we cannot really make these broad sweeping claims about beaches if we do not have a foundational understanding about how beaches in the Virgin Islands work and what their status is. So there really is a need for more basic information about the stability of beaches and their threats before we can make these alarmist claims. So that brings me to the purpose of this study. I want to build knowledge of VI beaches and their shorelines. I wanted to assess the stability of beaches, as well as provide a framework for an in-depth beach-specific analysis using Lindbergh Bay as a case study. So I'll talk about this later on, but Lindbergh was identified as an erosive beach in this study. So I wanted to do an in-depth analysis of some of the factors contributing to its vulnerability to try and understand why it's eroding so much. And then that framework could then be applied to other vulnerable or erosive beaches in the Virgin Islands. And then I overall wanted to increase data availability to help better inform management in the future. So there were 3 components to my project. The first being beach surveys, the second, a long-term shoreline change analysis, and then the third, that Lindbergh Bay case study. So I first want to start by introducing the beach surveys. I went to quite a few beaches across St. Croix, St. John, and St. Thomas, and recorded basic beach characteristics like slope, sediment samples, and beach profile features. I also recorded high watermarks and mean water level in the field, and we used a GNSS device for this as opposed to a regular GPS or just my phone, which means these were recorded with very high accuracy, which allowed me to then map them in ArcGIS and compare the distance between them to the 50-foot setback distance. In addition to this, I used the run-up equation from Stockton 2006 to determine hypothetical run-up values of different waves to help contextualize these high watermark values. The main factors that go into this run-up equation are beta F, which is the foreshore slope, H naught, which is offshore wave height, and L naught, which is the offshore wavelength. And I keep mentioning things like high watermark, run-up, and mean water level. What are these? So mean water level is essentially if the ocean didn't have any wave action going on and it was still like a lake, where would that water level be? If you went to the beach, you can kind of estimate where mean water level is by looking at where waves break and how they run up the foreshore and then retreat back seaward. Mean water level is somewhere in the middle of that. And then run up is the vertical height of water above the mean water level after a wave breaks. So this is measured in elevation. In the diagram, you can see the wave breaks, and that arrow is indicating that elevation above mean water level is the run-up value. Whereas high watermark is the signature of horizontal distance that run-up has reached on the beach. So wherever that water travels to on the beach, that furthest point landward, that is the high watermark. And this was identified in these beach surveys by finding a marine rack line of marine debris, things like seaweed, sea fans, anything you can identify that's from the ocean that has been washed up on the beach and pushed further landward is the high water mark. Well, why do these matter? They essentially tell us how much of the beach gets inundated depending on wave height and wave length. And that information can then be used to contextualize these current setback distance regulations. And maintaining effective setback distance regulations helps to ensure the delivery and regulation of beach ecosystem services like coastal protection, which is so important. So now I want to get into the results of these surveys. So the beach basics slope measurements, we observed a range of slopes from 7 to 12 degrees with an average of 9 degrees. When I talk about beach slope, foreshore slope, I'm referencing this area of the beach that you can see in the bottom 3 images of this slide. Foreshore slope is kind of hard to capture on camera. So these examples are more extreme. You wouldn't see these at every beach every day. And then sediment sizes ranged from 0.25 to 0.5 millimeters, which is classified as medium sand. And I would like to add that we know that the wave climates at most beaches in the VI are relatively moderate, and a slope of 9 degrees and medium sand is associated with waves that experience that moderate, with beaches that experience that moderate wave exposure. So this is consistent with what we did already know about beaches. And then we found also that the main source of sediment is coral skeletons and shells after looking at sediment samples under a microscope. Those 3 images on the right are examples of what these sediment samples look like under the microscope. There's kind of a yellow tint over them, but you can tell that they are derived from coral skeletons and shells that are broken up by wave action because it's mainly white and then there's bits of pink and brown that indicate shells. So now I want to get into the high watermark results. So this figure shows us high watermark locations on beaches compared to the actual beach width. So the red stars represent where the high watermark was found on the beach. Those bottom blue triangles represent the width of the narrowest portion of the beach. The top blue triangles represent the width of the widest portion of the beach, and 0 on the y-axis would be mean water level. So if we look at Brewers, for example, you can see that the narrowest portion of the beach is roughly 38 feet wide. The high watermark was recorded around 39 feet, and the widest portion of the beach is around 160 feet wide. One thing that sticks out on this figure is that the narrowest portion of all of these St. Thomas beaches were inundated by these high watermarks. And if we add in the context of the setback distance, which is this dashed red line, that is that 50-foot setback distance, we can see that a few high watermarks come very close to it. Hull Bay happens to exceed it. And for beaches like Sapphire, Frenchman's, and Vessup, they are not, like the widest portion of them is not even a full 50 feet. So their development could occur behind the vegetation line or natural barrier that was established in the Open Shorelines Act. So this figure kind of reveals that high watermarks are showing a lot of public beach being inundated, which can limit the enjoyment of a beachgoer's experience. This also could put potential development at risk, or development that's already there could be at risk for storms that might be causing high watermarks like this, or even just an everyday wave that could potentially lead to watermarks like this. Which brings me to my next slide, which is hypothetical waves and their run-up and high watermark values. We recorded these high watermark values, but we don't know exactly what types of waves cause them. So I use that run-up equation from Stockton 2006 and hypothetically determined potential run-up and high watermark values based on waves ranging from 0.5 meter to 5 meters tall. And I did these calculations based on the slope range that I found during my field work of 7 to 12 degrees. And based off of this, it seems like the high watermark values in the previous figure were likely caused by 3 to 5 meter waves, which is their offshore height. Excuse me. And those types of waves wouldn't be observed every day in the Virgin Islands. There are some beaches that will experience 3 to 5 meter waves in the winter due to swell events, and then other beaches would only see waves of this size during a storm. So that kind of gives context for what waves were causing the high water marks that I observed during my field work. But if we take a look at the 0.5 meter and 1 meter wave, we still see that the high water mark can be from anywhere from 6 feet to almost 11 feet back on the beach, which is a sizable chunk of that setback distance. So conclusions from the beach survey, we identified that beaches in the VI have a mild foreshore slope, a medium grain size, and a coralline and shell-based sediment composition. We also found that the narrowest section of every St. Thomas beach included in the high watermark surveys were inundated, and development there would hinder the public beach availability. Additionally, any development there is at risk in the event of a storm, and ecosystem services provided by that beach are also at risk. And then finally, a 1 meter wave had a hypothetical high watermark range of 10.9 to 10.89 feet in the Virgin Islands. This is potentially over 20% of that setback distance and more than 20% if the vegetation line is closer. So this raises some questions regarding the 50-foot setback distance, and definitely opens the door for more data collection in this area to help better inform future management. So now I want to move on to part 2, my long-term shoreline change analysis study. So I used aerial and satellite imagery to define shorelines for 1954, 2004, 2010, 2017, before and after hurricanes Irma and Maria. For those who don't know, in 2017, 2 major hurricanes hit the Virgin Islands back-to-back, hurricanes Irma and Maria. I also established shorelines for the years 2020 and 2022. I then imported these into a shoreline change software, USGS digital shoreline analysis system, and used this to calculate various shoreline change statistics. I also calculated very thorough uncertainty values for each year to improve accuracy, because you can't just draw out the shoreline using an aerial image and say, yep, that's exactly what the shoreline is. There is some uncertainty associated with that, and I'll get into that in the next slide. And then I also determined the weighted linear regression rate of change for each beach, which is essentially a yearly rate of change assigned to each beach from 1954 to now. And this software calculates various shoreline change statistics, but today I only have time to go over the WLR rate. And this screenshot on the right is an image of what the DSAS software looks like. The cluster of green lines in the center represents all of the different shorelines I imported into there. And then the lines that are going through them are transects that I cast through the shorelines. And essentially what the software does is it looks at where each transect intersects with the different shorelines, and it can calculate how much that shoreline has changed year to year and provide you with a bunch of useful metrics for that. So for calculating uncertainty, this table shows all the different shoreline years and the uncertainty values associated with them. The uncertainty is measured in meters. And what goes into the overall U, the uncertainty rate, is UG, which is the georeferencing uncertainty, UPD, which is the proxy datum uncertainty, and UD, which is the digitizing uncertainty. So the georeferencing uncertainty is to account for any errors that occur during the georeferencing process of these aerial and satellite images. So when an image is taken from a satellite or an airplane of a curved surface, it's not perfect, and you have to georeference it, which means overlaying that image over one that you know is accurate and looking for known landmarks in your aerial image and the accurate image and kind of matching them up in whatever software you're using. I used ArcGIS, and then kind of refit your aerial image to be more accurate. However, georeferencing does not make these images perfect. So I still had to account for uncertainty here. So in order to calculate that, I took L, which is essentially the distance between a location of a known landmark in my reference image, and then where it appeared in the aerial image. And then I took the average of all those values to determine the uncertainty, the georeferencing uncertainty for each year. Next is the proxy datum uncertainty. So the proxy datum is essentially what you use to establish your shorelines. In this study, we used mean water level. And again, if you're taking a picture from above, a 2D photo of a 3D surface, things like tidal variation and the degree of the foreshore slope can impact where you think the shoreline is. So you might identify it as one place in the photo, but because of slope and tidal variation, it's slightly off. So in order to calculate this, I looked at DHQ and DLQ, which are the mean diurnal high water inequality and the mean diurnal low water inequality, which are tidal datums that can help you account for where the water is throughout the day. The Virgin Islands has a very small tidal variation, so this wasn't a very high number. And then the bottom portion, tangent of beta, which is the average beach slope. I used the average slope of 9 that I found from my field days here. And then finally, the digitizing uncertainty. This is applied to aerial images as opposed to satellite images. Aerial images are taken out of an airplane. And this was only applied to 1954 because it was the only aerial image, the rest are satellite. And I just used a standard value of 1 meter as recommended by USGS. This entire uncertainty process is based off of USGS papers that were used to assess shoreline change in the Pacific Northwest. However, the beaches of the Pacific Northwest are very, very different compared to the beaches of the VI. So I tweaked their processes and equations a bit to better match the beach characteristics of the Virgin Islands. So finally, we can get into the results. So this plot shows these WLR rates with uncertainty for St. Thomas. The bold line in the middle is 0. So if a beach's rate was 0, that means there's no change year to year from 1954 to now. If the WLR is positive, that represents an accretive rate, that beach is growing from year to year. If it's negative, erosive, that means it's shrinking from year to year. So on this plot, the green dots are accretive, definitively accretive with uncertainty considered. The red dots are definitively erosive with uncertainty considered. And the black dots are just uncertain, and that is because the magnitude of the WLR rate is larger than the magnitude, is smaller than the magnitude of the uncertainty rate. So if you look at Margaritaville, it's extremely erosive. That rate is very low. However, its uncertainty is really high, and because it passes above that line into the accretive zone, we can't definitively say, yes, Margaritaville is an erosive beach. But I do want to mention that Margaritaville was the most erosive beach of any included in this study, and that is largely because it's a nourished beach, which means as it erodes, they add more sand to help bolster the width of the beach. But when you add sand in that doesn't perfectly match all the other sediment characteristics of that area, it can be eroded very quickly. So that's what's happening at Margaritaville, and that's why its WLR rate is so erosive. And I also do want to highlight that Lindbergh Bay is one of the definitively erosive beaches identified for the St. Thomas shoreline change analysis. So now I'll go over St. Croix. The first thing that sticks out is the uncertainty rates are much lower for St. Croix. We also have more definitively erosive beaches here coming in at 5, and then 1 definitively accretive beach. For St. John, the uncertainty is also high. We have 2 definitively accretive beaches and 1 definitively erosive beaches. And now if we look at all of the 3 islands side by side, we can see that there are more erosive beaches than accretive beaches. And I also kind of wanted to point out a pattern I noticed with the uncertainty. So looking at St. Thomas and St. John first, St. Thomas and St. John are located both in the Atlantic Ocean and the Caribbean Sea. Their northern coasts are exposed to the Atlantic Ocean, their southern coasts are exposed to the Caribbean Sea. And a lot of these beaches on those 2 islands with higher uncertainty rates are those located along the north coasts. Now these beaches are exposed to swells from the Atlantic. However, they are sheltered by the neighboring British Virgin Islands. So the swells that they do experience are highly episodic, and this can lead to periods of lots of erosion and then lots of accretion, which equals a very dynamic beach. And if you look at the ways in which the DSAT software calculates the individual uncertainty rate associated with each weighted linear regression rate, it shows you that the more dynamic a beach is, the higher that uncertainty rate is going to be. So if we look at St. Croix, which has much lower uncertainty values overall, St. Croix is located all in the Caribbean Sea. It's not touching the Atlantic. and has no neighboring islands. So while it has an overall more powerful wave climate than St. Thomas and St. John, it's a lot more predictable. They don't experience the same episodic swells that St. Thomas and St. John do, which leads to overall less dynamic beaches, which is why I believe it has lower uncertainty values. And then I wanted to plot them all on a map. Even though this doesn't show uncertainty, it's still interesting to see some patterns. The cooler colored dots represent accretive beaches. Warmer colored dots represent erosive beaches. You can see St. Thomas is, the northern side of St. Thomas is very accretive. On the east end of St. Croix, we see some accretion. Again, these numbers do have to be taken with a grain of salt because uncertainty isn't applied here, but this is still an interesting way to look at these rates. And then the territory-wide WLR rates by the numbers. I did calculations for St. Thomas and the whole territory with and without Margaritaville because it does have such a huge impact on those rates. For St. Thomas, we can see that it's mildly erosive, but when we take out Margaritaville, it's mildly accretive. St. Croix, mildly erosive. St. John, mildly accretive. And then overall, the whole territory is mildly erosive. But again, these uncertainty values are larger than the rates themselves. So this is something that has to be taken with a grain of salt, but it does suggest that beaches in the territory are slowly eroding. Conclusions for the long-term shoreline change study. Beaches seem to be slowly eroding, but uncertainty makes it difficult to make large sweeping claims about the territory, like, oh, all of the beaches are going to be gone by 2050 because of sea level rise and hurricanes. Of the beaches that were definitively eroding and accreting, more were eroding. There were 8 total definitively erosive beaches and 4 total definitively accretive beaches. We found that shorelines in the VI are highly dynamic, and more shoreline data needs to be collected moving forward in order to help reduce uncertainty and just get higher quality data. So now I'm going to move into the Lindbergh Bay case study. So why did we select Lindbergh? So first, it was identified as definitively erosive, as I've been over. There was also extreme sand loss in front of a rock revetment there after Hurricanes Irma and Maria. After Hurricane Marilyn hit St. Thomas, the road behind Lindbergh was inundated and there was a scour there, and that happens to be the only road that leads to the airport on St. Thomas. This is obviously extremely important to protect, especially in the event of a major hurricane. So a rock revetment was built. However, after Irma and Maria came through, all of the sand that was in front of the revetment eroded and it has not come back to this day. There is also a large dredge hole near shore that could be impacting the wave climate as well as sediment transport. In the 30s, when the airport was built, they needed dredge material to fill in the marshy land that the airport was built on. So they dredged Lindbergh Bay to get that material, and the dredge hole is still there today. And number 4, Lindbergh is also highly developed, making it vulnerable to coastal squeeze. So this is an aerial image of Lindbergh, the star sitting on top of the hole. You can see where the hole is. That area is obviously a lot deeper than the areas around it. You can also see how developed the backshore of Lindbergh is. There's a lot of gray infrastructure there. And if you look at the sand going from east to west, starting on the east side of the beach, you can clearly see the beach, clearly see the sand. And then as you move west and hit that patch of trees, you can see the sand starting to disappear. And that is exactly where the revetment is. And this becomes more clear when we look at a shoreline change map. So this was a map I made using, trying to move this.
Could you do more? There's hide floating controls.
Thank you. Sorry about that, everyone. Okay, so this is a map that shows shoreline change and recovery at Lindbergh, pre and post Irma and Maria. The green line represents the shoreline at Lindbergh before the hurricanes. The red line represents the shoreline at Lindbergh after the hurricanes. And the blue line is the 2022 shoreline. So starting on the east end of the beach, you can see it wasn't too badly eroded in the storm and it recovered. As you move towards the center of the beach, there's more recovery. There is an area in the center of the beach where the beach did not recover fully, but the shoreline is mostly back to where it used to be. And finally, as we get to the eastern portion of this map, you can see that there was no recovery at all after the hurricane, and the shoreline is still where it was after Irma and Maria came through. And that's right in front of the rock revetment. All of that sand was lost. So the different components of this case study. First, I wanted to assess the impact of the hole using a 1D wave model, and then move into a 2D wave model that I used Delft 3D wave for. I also wanted to calculate the volume of sand walls at Lindbergh using digital elevation models, or DEMs. DEMs tell you the elevation of the Earth's surface, and if we zoom into the beach at Lindbergh and the elevation is at one point, the DEMs I use for this are from 2007 and 2018. So if you look at the elevation of the beach in 2007 and in 2018, it's lower, that is because sand was lost. So this is an oversimplification of the process, but I essentially calculated the total elevation of the beach in 2007 and 2018, and then subtracted that 2018 value from 2007 to determine how much sand was actually lost. I also wanted to assess the stability of the revetment using Hudson's equation. So this is Hudson's equation for the armor layer that gives you the W50 of a rock revetment, and the W50 is what the weight of the middle 50% of rocks in that revetment needs to be in order to protect everything behind it. And the components of this equation are WR, which is the unit weight of stone, and SR, which is the specific gravity of stone. I found out that the revetment at Lindbergh is made out of basalt, and there are just standard values for basalt for its unit weight and specific gravity. KO is the empirical coefficient. There is also a standard value that you use for this equation when you're looking at riprap style revetments like the one at Lindbergh. Theta is slope. And then finally, H is the design wave height at the toe. This was the tricky part. So this is determining what size of a wave the revetment is supposed to be protecting against. And in order to determine this, I wanted to simulate an Irma level storm because that's the storm that took the sand away from the front of the revetment. I did simulate one that passed St. Thomas to the south. In reality, Irma passed to the north. But I was able to come up with the design wave height using these calculations. So first, determining the storm surge, which is essentially how much the water level rises in the event of the storm. This is comprised of the barometric surge and the wind setup. And then determining the actual hurricane wave height using the maximum wind speed and the hurricane-induced fetch. And fetch is the distance over which wind can blow interrupted to help propagate waves.
Those are offshore.
Yes, and offshore wave height. When I reference wave height in this presentation, I'm talking about the offshore wave height. Waves will get smaller as they approach shore. So I also keep talking about these potential impacts of the dredge hole. What does that mean? So the presence of the hole may be limiting dissipation and causing waves to break with more energy at the shore. So when waves enter a bay like Lindbergh and start interacting with the shallow water, that means they are interacting with the seafloor. There's friction happening there. So the wave enters the bay and the water gets more shallow and it starts to essentially feel the bottom, and there is dissipation due to friction there. And this results in the wave height decreasing. And then as it enters even shallower water, another process called shoaling occurs. And this happens when the wavelength has to shrink, and as a result, the wave height increases. And then once the wave height reaches a certain point, the wave becomes unstable and it has to break. There is something called the steepness ratio, in which the height of a wave cannot exceed 78% of the water depth that it's in. Once it exceeds that ratio, it becomes unstable and has to break. And so with the presence of the hole, less dissipation theoretically could be happening because waves are not feeling the bottom because it gets deeper. Waves begin to interact with the seafloor when the depth reaches about half of the wavelength. So the hole is 35 meters deep. This means that waves with a wavelength of 70 meters in a period of about 2.7 seconds would experience dissipation there. That's a relatively large wave. The depth without the hole is 20 meters. So waves with a wavelength of 40 meters in a period of about 2 seconds will begin to experience dissipation there if the hole were to be filled in. And although I didn't do a sediment study as a part of this project, the hole could be storing sediment pulled out by the undertow. So when a wave breaks, a current called the undertow occurs, and this is essentially just pulling sand seaward. And normally there are processes that help to redeposit that sand on the beach, but if the undertow is pulling the sand into the dredge hole, it can't be pulled back out and redeposited onto the beach. And this image on the right is another aerial shot of Lindbergh Bay, as well as the transect that I'm going to propagate waves across in the 1D model. So jumping into the 1D model, this is the bathymetry that I pushed waves over. 0 represents offshore and 800 represents the shore where waves will break. The blue line is the current bathymetry at Lindbergh with the hole, and then the red line, the orange line, is the modified bathymetry where I filled the hole in. So this is what I'm pushing waves over, and we'll be able to see the differences in waves that pass over the hole versus the filled in. So I wanted to start with a 1 meter wave. That's something that could be observed in Lindbergh regularly. Again, 1 meter is the offshore height. And this subplot, the top plot is wave height, the middle plot is dissipation, and the bottom plot is water depth, just to remind you where the hole is. And there is essentially no difference between the waves passing over the hole and the waves passing over the filled in hole. And that is likely because a 1 meter wave is too small to have that 40 meter wavelength that would allow it to interact with the bottom, even if the hole was filled in. So this tells us that the presence of the hole at Lindbergh is likely not impacting the everyday wave climate, but maybe if the waves are larger, like in the event of a storm, we'd see a difference. And we do. When we run a 3 meter wave through the model, we can see on the top that the wave passing over the hole has a larger wave height and ultimately breaks at a larger wave height. If we look at the middle dissipation plot, you can see that the wave passing over the hole does not experience any dissipation until it gets out of the hole. So that means any dissipation due to friction that would be happening there is not because of the presence of the hole, and this leads to more dissipation when the wave breaks. If you look at the wave that's passing over the filled-in hole, the height decreases as it passes over the area where the hole is filled in, and you can see an increase in dissipation as well. That's due to friction. It's interacting with the bottom, dissipating energy, and it ends up breaking at a smaller height and dissipating less energy near shore when it does ultimately break. If you look at an even bigger wave, a 5 meter wave, we see the exact same pattern, but just more extreme. There's more dissipation happening for that wave that passes over the filled in hole. And again, no dissipation due to friction happening when the 5 meter wave passes over the hole. And when the wave that passes over the hole breaks, it ultimately breaks at a larger height. Well, what does this mean for the beach? And I wanted to contextualize this information using an erosion index, I. And I consists of the energy flux, which is how much energy a wave has as it propagates towards shore. And I multiplied that by the ratio of the undertow and the bottom orbital velocity. I've been over what the undertow is, and the bottom orbital velocity is how fast the water particles underneath the wave are moving. And so I took a time series of Paracu's forecasted waves for the south shore of St. Thomas, which is where Lindbergh is located. And then I also took, for each of these waves, the average of the erosion index in the surf zone. I identified the surf zone by looking at the point at which dissipation due to breaking was highest, all the way until the end when the wave is fully broken. So the average of the erosion index in that area to get the values for this plot. And this time series has waves that are very small and waves that are very large. And you can see that for the smaller waves, there is no difference in the erosion index, whether there's a hole present or not. However, as the waves get larger, we can see a difference in the erosive ability of the waves becoming a lot more dramatic around waves of about 3 meters. So this prompted me to want to investigate further and conduct 2D modeling. This uses SWAN, which includes more physics than the 1D calculations. So my predictions going into the 2D model based on the 1D results are that the hole is going to impact shoaling, dissipation, and wave height around a height of 3 meters. And waves 3 meters and larger are likely going to exert more erosive force on the shore when breaking. So this is the overall extent of my grid for the project. The dark blue areas represent land. And you can really see everything that's happening kind of on the southwestern shore coast of St. Thomas here. This is a screenshot of what the entire grid looks like when I push a 5 meter wave across it. And it's very interesting, but we really care about Lindbergh. You can see an arrow that is pointing to the transect that I'm going to show you the values plotted along. It's the same location that the transect was in my 1D model, so it's a nice direct comparison. I ran 1 meter waves with this model and it showed me the same as the 1D model. There's really no difference. So I'm just going to focus on the 3 meter and 5 meter waves here. These plots show wave height. I do apologize, they're flipped from the 1D model. So 0 is where the wave breaks and 800 represents offshore. The 2 stars on the x-axis represent the location of the hole. So you can see how it's impacting wave height. For the 3-meter wave, the plot on the left, you can see that the presence of the hole lets the wave become a larger height, but it ultimately breaks at the same height as the wave that is passing over the filled-in hole. There is a very steep decline in wave height though once the wave gets out of the hole, which could potentially lead to the wave breaking more forcefully. And we look at the 5-meter wave, it looks very different to what we saw in the 1D model. As it's passing over the hole, the wave is taller than the wave that passes over the filled-in hole. However, it does ultimately break at a lower height. But again, that very steep drop in wave height as the wave exits the hole could be contributing to how forcefully this wave breaks. So with this software, I wasn't able to calculate an erosion index, but I was able to look at wave-induced force, which is essentially how much force a wave exerts on an object in its way. And looking at the wave-induced force for the 5-meter wave side by side with its wave height, we can see that that rapid decline in wave height does cause the wave passing over the hole to have higher levels of wave-induced force. And there is a peak right at the point where the wave begins to break. So this tells us that perhaps that sharp decline in height is leading the wave to break more forcefully, and the hole is still contributing to more powerful, more erosive waves. And if you look at the area under the curve, the wave-induced force of the wave that passes over the hole had roughly 70 newtons per meter squared more erosive force than the wave that passed over the filled-in hole. So in storm situations, that's when you would see a 5-meter wave at Lindbergh. The presence of the hole could be contributing to more erosion. More modeling in the future with a more refined mesh, as well as using a non-linear model, could help to confirm this. So now I want to get into the revetment and the sand loss that occurred there. So for 2007, the total sand volume was about 14,236 cubic meters. By 2018, that was down to 8,745 cubic meters, resulting in a total sand loss of 5,491 cubic meters. And majority of the sand loss was directly in front of the revetment. And I do want to mention that this 2018 DEM was recorded 3 to 4 months after Hurricanes Irma and Maria. So Lindbergh had made a recovery at that point, but not a full recovery. However, I think it's still fair to compare this to today because Lindbergh still has not recovered and the sand in front of the revetment has not come back. So this amount of sand loss is concerning. And I just kind of want to refresh our memories on why we're looking at the revetment. Erosion and scour in front of revetments isn't uncommon, and using incorrect sizing of rocks can lead to increased wave reflection and energy that would lead to increased erosion and kind of prevent sand from being deposited there. And I used Hudson's formula to determine what the weight of the middle 50% of rocks should be. So this is kind of a snapshot of how I did the estimations of the weight of the rocks that are currently in the revetment. So I was able to take a LiDAR scan of different rocks in the revetment and then import them into a software called Blender. B is the isolated boulder in Blender after I trimmed everything out around it. And C shows all the little vertices that were picked up by the LiDAR scan, just to show how detailed this is. And it looks 2D here, but it's 3D. And I was able to make the rock watertight, which allowed me to determine the volume. And since I know that this is made of basalt, I know the density. Using volume density, I can determine the weight. So Hudson's equation showed me that the W50 required for the revetment is 4,733 pounds. And the weight of the largest rock I found in the revetment was about 2,039 pounds. So these rocks are likely too small, and the airport road would be vulnerable to inundation and scouring in an Irma level storm, again, that passes St. Thomas to the south. In reality, it passed to the north, so it wouldn't have been as extreme as the situation I simulated here. So conclusions from my Lindbergh assessment, most sand loss occurred in front of the revetment. This could be caused by increased reflection due to waves and design flaws at the revetment, or perhaps more forceful waves due to the presence of the hole, or a loss of sediment supply due to sand settling in the hole, but it is likely a combination of all of these factors. And then the sand loss in front of buildings in the middle of Lindbergh could be a result of coastal squeeze. And there's a need for future research that includes nonlinear modeling as well as a sediment study. My overall final takeaways from all components of the project, the high watermark study revealed that inundation is limiting public beach access, and there is evidence to support the need to revisit the 50-foot setback distance regulation, as well as collect more data to help support future policies relating to setback distance. This study provided the first assessment of beach stability that included uncertainty. And it showed us that beaches could be slowly eroding, but we really do need more frequent data collection in order to reduce uncertainty and make more definitive claims about the status of beaches in the Virgin Islands. And then finally, this study identified concerns at Lindbergh and investigated how they contribute to the beach's overall vulnerability. The hole does appear to be altering the wave climate there. The revetment could be improved, and ideally, this study could be repeated at other beaches that are identified as erosive in this study. And I just want to say thank you to my committee, my advisor, Greg Winnell, my other committee members, Legna Torres Garcia and Hillary Lohman. I couldn't have done this without your help and guidance. I want to thank all the research support from everyone in CGTC. I appreciate you so much, as well as my funding sources that made this resource possible: VIF Score, the National Science Foundation STEM Scholarship, and the Lonavento Charitable Trust, and of course, all my wonderful friends and family. So thank you, everyone.
Thank you. Thank you, those here and those online. Now it's time for questions. So please do not write your questions in the chat. Just go ahead and mute yourself and ask the question. Anybody here want to ask a question? Anybody online?
Zoe, this is Marlon Hibbert with DPNR, CZM. Thank you. Excellent presentation and research. I hope you consider continuing the tidbits that you say we need to continue to do. So I hope after you successfully pass this stage that you will consider staying and continuing that research along with the guidance of Dr. Guanel and others. So with Lindbergh, because of its known importance, we know that in 2017, it seemed to have been the point at which it lost most of the sand. Did you factor in that period of time between then and now, that we also had the very surprising Dorian in 2019, and then I know your data collection would have extended to 2024, but then we had Ernesto as well in 2024, and it seems so likely it's been eroding, but we've had in less than a decade 3 or 4 very significant events that contributed to that. What are the implications of the increasing frequency and intensity of storms as it relates to Lindbergh in particular? And and again, I don't want to ask you these if-what questions, because you have a lot more research to do, but just preliminarily, in your expert opinion, because now you are an expert, do we need to be concerned? Because this is the only in and out road that connects the airport.
Yeah, so the increasing frequency of storms, specifically at Lindbergh, is concerning. If the sand in front of the revetment has not recovered, I'm sure that the hurricanes that have hit St. Thomas post Irma and Maria have played a role in the sand not returning. But one thing I do want to mention, as part of the shoreline analysis that I did, as well as other members of CGTC did, it showed that a lot of other beaches in the territory were able to make a full recovery after Irma and Maria, despite the storms that happened afterwards. So this is indicative of external forces at Lindbergh preventing the sand from resettling there storms definitely play a role in there, but there's also something else that's going on from preventing the sand from coming back. And if these storms keep coming, it's only going to make the situation worse. And then for the second part of your question is the airport road at risk. I would say it is concerning, especially with the loss of sand in front of the revetment. The sand there was also helping to attenuate waves in the event of a storm, and without it there, it further weakens the ability of the revetment to prevent inundation and scour. So I think it would be wise to perhaps reevaluate the revetment and see what improvements could be made there. Yeah, those are my thoughts on that. Thank you for your question.
Okay, thank you. Were there any? So from the eastern side, and again, I'm going back to Lindbergh because it's such a management challenge for us. I'm deliberately staying away from the 50-foot setback discussion right now. But the movement of sand, was there any longshore drift from the eastern side of Lindbergh Bay to the western side? And so, whilst your graphic seemed to say that the eastern portion is fairly stable and recovered very well actually after the 2017 storms. Do you think we need to additionally record if there is a significant drift of sand from east to west? And because as soon as it reaches that western boundary, it's disappearing. If eventually the sources, so the sources of sand to Lindbergh, to the eastern portion, if there is a way in which we can hypothesize, predict the rate of movement of that drift of sand, if there is one, to the western side and continuing loss because it's slowing off. I know I was going to ask the question and then you responded in a few of your statements about setting up a sediment trap at the either on the slope of the dredge hole or on the bottom of the dredge hole. I did want to ask, did you actually dive it?
I did, so this past weekend, I went and snorkeled and looked at the hole, and there's a lot of trash and debris in it. I couldn't quite tell if there's a bunch of the sediment accumulating in the bottom because of the trash on top of it. And a sediment study wasn't included in my project, so I can't be sure about the longshore drift or what the longshore currents in Lindbergh do look like. I do have an idea about why that eastern side of the beach is recovered so well after the storm and was also not as badly affected by Irma and Maria as the rest of the beach. When I was doing my 2D modeling and pushing waves into Lindbergh, it was really hard to get them to propagate all the way to the eastern side. And the way that the entrance of the bay is set up and with the waves approaching from the southeast, there is just less wave action that happens in that corner of Lindbergh. So that's part of why it didn't erode so badly during the storm. I can't answer the question about longshore drift because I didn't record any data regarding that. But I would say the eastern side of the beach is in a better place than the western side. I'm not sure if the eastern side is losing sediment to the western side, but that's definitely a very interesting avenue to pursue in the future.
Would you be able to see from your data that you used for the long-term shoreline chain analysis, would you be able to see that you have an accumulation of sand on one side?
Off the top of my head, I can't remember if the transects.
Would you be able to see?
Yes, I could look at the transects on the eastern side of Lindbergh and see if they are accretive compared to the western side.
But just from the aerial imagery, can you see if things are in general going in one direction?
You could see if you looked at the aerial imagery, because the width of the beach on the eastern side would be growing or shrinking, and then the width of the beach on the western side would be growing or shrinking. And if one side grew while the other shrank, you could make the assumption that sediment has passed from one side to the other.
And did you see that? Did you see the eastern side keeping growing?
No, the eastern side has mainly stayed the same. So it looks like the eastern side is not necessarily accreting, but it's remaining stable. So that could indicate that it's potentially accreting, but losing a lot of sand to the western side through longshore drift, and that sand is then being eroded away. Or it could just indicate that the eastern side of the beach on its own is stable and nothing is happening there, erosion or accretion wise.
Remember about the hole. Right, so large wave can take that sediment, move it offshore, and the hole is a sink, because
Yeah.
then the smaller wave cannot really move that sediment because
Yeah.
it's so deep.
So it would
It's
take
almost
the
like a
storms,
small
yeah,
canyon.
yeah.
So sediment can be lost. I think sediment is lost by the cross-shore movement of sand falling
Into the
into the
hole.
hole and the small wave, because that's what you found, right? Larger wave, the undertow, when they break over the hole, it means the current can move it.
Yeah,
But if it's a smaller wave,
it can,
it can't.
yeah. And that's what is mainly happening on the rig, is those small waves.
So the hole might be a net sink, and so the fact that you found trash in the hole
Yeah.
means that things get trapped.
Mhm.
And the idea of putting sediment traps in the hole, or looking at sediment accumulation in the hole, or regular bathymetry of the hole after, would give us a sense of what's happening.
Yeah, taking a regular bathymetry scan of the hole would be really interesting to see if it's slowly getting shallower as a result of sediment piling up inside of it.
Right. So that's an interesting concept, because anecdotally, we've always heard fill it back in wherever we're getting, if they are dredging projects within the territory, to utilize that hole as the receptacle for the dredge material. There's been certainly, and with reason, uh, opposition to that because of the magnitude of the hole. Nobody really knows how much it's going to take to fill it, or to get to that threshold. You the size of the threshold, the wave run up. What is that threshold that would counteract that sink that it is potentially right now doing, or serving as? What is that threshold that it would now start to reverse that situation, where it instead of a sink, it acts as a repository for sand? I'll ask one more question. So I know you said it, that a lot more research needs to be done and data needs to be collected regarding revisiting the 50-foot setback. In North Carolina, there is every 5-year bit of work that they use a sliding scale. So in some regions where there is, known accretion or recorded and documented accretion, as opposed to erosion, that setback is on a sliding scale. So if the previous 5 years showed an accretion, then that setback, in terms of development pressures, can be reduced, because you have land accreting, or sand or beach area accreting, where you have an overall erosive situation. Then the setback is increased, and it depends on the size of the building. So if you're doing a 1,000 square foot building, then your setback remains at 50. But if your threshold meets 3,000 square feet, then it's 1.5 times, which would put you at 75 feet. Sorry, at 100 plus feet away from that high water mark. So I'm thinking that, again, I'm encouraging and asking the questions and putting it out there that you stay with us. Don't just disappear on us after you've gotten your master's degree, which I'm sure you're going to get. Congratulations again. But that seems like an additional amount of work that we will need to help us make the management decisions. But I do want to congratulate you on a job well done, and very, very well done. So thank you again. And thanks to your committee members as well, and all your support staff. Team, sorry.
Thank you. I really appreciate that, and I agree that beaches are very dynamic, and the policy surrounding them should be equally as dynamic. So I think that idea in North Carolina is cool.
Any other question?
Yes.
Yes, go ahead.
Okay. But Zoe, congratulations and thank you for choosing the Virgin Islands University here particularly for your studies. Approximately, what is the distance of this hole, this abyss from the shore to, how far out is it?
So I'll repeat the question for those on Zoom. The person asked how far out is the hole from the shore, and then what is the extent of the hole? The hole is about 100 meters from the shoreline. It is 35 meters deep, and it's about 350 meters long and wide.
So 100 meters is 300 feet, more or less. 30 meters deep would be 100 foot. Something like that.
Yeah, it's very sizable.
Any other question?
Any other questions from those on Zoom?
What's your overall take on the values of erosion of the beach, uncertainty taken into account?
I feel that even with taking uncertainty into account, I think the overall WLR rate of change for the territory with Margaritaville is negative 0.04. Without Margaritaville, it's negative 0.01. And just from all of the field work I've done, going to the beaches over the course of 2 years, in the summer, in the winter, seeing them in different seasons, I feel like that mild erosive value is pretty accurate to what's happening. Just because it's taking into account what's going on at all the beaches in the territory. And I observed some beaches that were accreting every time I went. I also observed beaches that were eroding every single time I went. So I think the overall status in the Virgin Islands is slightly erosive, but for now, relatively stable. And there's really no need to panic or be worried about major beach loss in the coming decades. But again, this claim would be much more.
And what do you think are the main worries potentially for Director Gilbert when it comes to beaches in particular?
I think the main concerns would be certain beaches slipping through the cracks and experiencing extreme erosion that is going under the radar because there's not regular monitoring happening. Like Manning Bay on St. Croix is eroding extremely rapidly. I feel like every time I went there for field work, it looks worse. There's also a house there that's about to be in the ocean, which is extremely concerning. So without regular monitoring, things like that can occur and nothing is being done to help prevent the erosion happening there. And I do also think the setback distance, more data needs to be gathered relating to that and fast, because in the coming decades, we are going to see sea level rise. We are going to see worsening storms, and having larger setback distance would help better prepare beaches for that. And in order to create a more adequate and effective setback distance policy, there needs to be more data. So I think really just getting on top of data collection when and wherever possible.
All right. One last chance for questions. Yeah.
Would you know if DPNR is in the process or doing any kind of preventative measures or remedial activity to shore up, Lindbergh Bay to prevent that erosion from continuing?
The question was, do I know whether or not DPNR is doing anything at Lindbergh Bay to help mitigate the erosion that's happening there? I believe things are happening. I'm not exactly sure of the details. I know people want to do a sediment study. I'm not sure if it's off the ground or happening, but I know that it is on the radar of DPNR and they are certainly working on it.
So I'll provide a bit of a response to the question. Since I'm with DPNR and we're very pleased to partner with UVI and Zoe and Dr. Gwanell and his team on this project and continue to support other projects that are continuing to collect additional data. We have engaged the Army Corps engineers, we have engaged Public Works, and we have engaged the Virgin Islands Port Authority in looking at this concern that we have. Your specific question says, what are we doing? Not a lot that we can do. It is costly. We do not have enough information. As an example, Zoe mentioned several times during her presentation the need for additional information. What are the intervention measures? You know, anecdotally, she said, you know, larger stones. So, you know, even conservatively, to remove what's there and to replace with larger stones will be a multi-million-dollar project just to protect the roadway. Doesn't solve our erosive problem because larger stones also mean still the same sand loss or greater. Well, no, not according to Zoe's research. But certainly, you know, very costly. And so we've engaged the Army Corps of Engineers. Miss Lohman, who had her hand up, can speak to that a little bit more. But we are tracking what we hope that from Dr. Guanel's research and Zoe's research as well, is that the territory will have a way moving forward where we can implement a consistent monitoring plan for all beaches across the territory. So this is seminal work for us, because what Zoe and the team here has done is setting the groundwork or the framework for us to acquire equipment, acquire the technology, acquire the standard operating procedures, acquire the data collection, the data analysis skills to continue to monitor these situations across the territory. So it's very good work for us from a management perspective. This is exactly what we need in order to make detailed, informed decisions. You know, anecdotally, everybody says, notice Zoe was very coy in her word selection. She said, you know, there's some erosive and there's some accreting. You know, mildly erosive is kind of what she said. You speak to anybody, usually the local population who are heading to the beaches year in, year out, have been here, going there from they were small, they're going to tell you all the beaches have eroded. The data doesn't say that, but again, human perspective, human opinion. So we take it seriously, and we are very happy for the research and the information that we're going to get from it. And we're just, again, I'm going to make the public plug. Don't leave us just yet. I smell a PhD. I leave it at that.
Thank you. Any more questions from anyone?
All right, well, thank you, everyone. Now it's Zoe and like 99 and Larry. So
Great
wish
job,
you luck.
Zoe. Congratulations.
Thank
I'm not going anywhere.
Well,
Just
yeah,
wanted to
don't-
say
don't-
that.
don't-
Just wanted to
Don't
say
be too
that.
fast, Hilary.
Congratulations.
You have to do your role of greeting her for the next half hour. Well, thank you, everyone. Hilary and Legna, please stay online. But thank you, everyone, and see you next time.
Thank you, everyone.
Thank you. It was wonderful to listen to. Congrats.
All the good stuff.
I saw all the equipment.